Ground effect vehicles, or Ekranoplan's, are an interesting type of flying vehicle that leverage unique aerodynamics while close to the ground to increase efficiency. When a wing is close to the ground, the drag from wingtip vortices is reduced and an air ramming effect under the wing increases lift. The result is an increased lift-to-drag ratio the closer you get to the ground and a negative feedback loop that self-stabilizes in the ground effect cushion. Now, I'm not an expert in RC Ekranoplan's, and I'm certainly not the first to do it, but when Kavin from dRehmFlight reached out asking how we can take one of his already impressive autonomous Ekranoplans to the next level, I was immediately interested in helping out. I'm just going to cut right to the chase. We're going to be adding computer vision to Kavin's ground effect vehicle so it can autonomously follow behind him in his boat. He assured me that this 100% was not a part of his plan for world domination, and he seemed like a nice guy, so I believed him. Daniel and Sebastian from RC Testflight have been working hard on a flight controller system implemented in ArduPilot to help stabilize the vehicle in ground effect. This is the same code that's on Kavin's Ekranoplan. Earlier I mentioned that ground effect is a self-stabilizing effect, but for vehicles this small with such low inertia, some additional feedback control with a lidar altitude sensor is kind of required, since the lightweight models we're flying are so susceptible to disturbances like wind gusts. So when tuned well, this ground effect controller they developed essentially turns an RC airplane into an RC car. Just throttle and turning control is required to maneuver around. To test my flight computer and computer vision algorithm before sending it out to Kavin to play with, I needed to build my own Ekranoplan with a similar control system first. So I drew up a quick design, started cutting foam, and stuck it all together with hot glue and packing tape. I wanted a lot of pitch control authority, so the horizontal stabilizer is almost as big as the wing on this platform. As I mentioned, this vehicle technically doesn't need a flight controller to fly in ground effect, but I'm using my open source flight controller dRehmFlight, which runs on a Teensy 4 microcontroller to eventually imitate the functionality Daniel and Sebastian built into the flight controller on Kavin's platform. I was excited to be done with the baseline build, so I took it out for a quick flight just to test angle mode in my flight controller. No ground effect control implemented just yet. This platform has ailerons for roll and 2 elevators for pitch that can also help in roll control. This technically makes them elevons. For yaw control, I have differential thrust mixed in. I took it up for a maiden and it flew really well without any tuning, but the wing was still a little floppy even with a 5mm carbon spar. Still, I was really happy with how this design flew, especially considering that it was almost completely eyeballed. So I went home to add more foam to the wing to thicken it up, and went out to fly again the next day. I wanted to spend some time tuning my baseline flight controller on this vehicle before adding the ground effect altitude hold capability, and then the computer vision autonomy later. I got the angle mode PID controller tuned really well and started to fly in ground effect manually, which was a little tricky, especially with the wind. Despite the wind, my angle controller handled it pretty well and I had some fun with it.
A little bit of a headwind there. VTOL!
By the way, when I say angle controller, what I mean is that the inputs on my radio are mapped to desired roll and pitch angles between about -30 to 30 degrees. This is different than, say, a racing drone, which maps radio inputs to angular body rates, so they can do flips. Or maybe a pendulum balancing drone, which maps radio inputs to pendulum angles. But back to the Ekranoplan. Just when I was about to call it a successful day, my depth perception failed me, and
I had the one job of not hitting the 2 light posts in this parking lot. I think the wing and most of it is fine. I just gotta rebuild the fuselage. Oh no, don't blow away.
So I took the wreckage home and glued it back together with a new nose, and it was almost as good as new. I figured since I had it tuned well before the crash, now was a good time to add the lidar sensor and ground effect altitude hold capabilities. The code to do this is actually pretty simple. The lidar sensor measures the distance to the ground, and I use that in a simple PID controller with a fixed altitude set point of about 20 centimeters. The controller code basically just computes a stabilized variable that I can then assign to the servos or motors in my control mixer. So I mapped this variable to act as flaps or spoilers to increase or decrease lift based on if it was below or above the 20 centimeter altitude set point. That's a lot of words, but basically flaps go down when too low and flaps go up when too high. The flaps naturally create a little bit of a pitching moment, so I mixed in a little elevator to counter that as well. Finally, I mixed in a bit of throttle, more throttle when the altitude was too low and less throttle when too high. But overall, I wanted the flaps to dominate the altitude control so throttle could correspond to speed later. Right off the bat, the lidar and altitude controller worked pretty well, but I was cursed again by wind, so I could only fly in one direction into the wind in this relatively small parking lot. Still, it was cool to see the altitude control working while I was giving no pitch or throttle input on my transmitter stick. It was getting dark, so I went home and prepped for some more ground effect flights later in the week, but not before completely butchering the paint job. I found a bigger parking lot and day with less wind and put my Ekranoplan through its paces. I found that quite a lot of damping or degain really helped maintain altitude and reject disturbances from the wind. I quite literally started flying this thing in laps around the parking lot exactly like an RC car. Absolutely no elevator or rudder control required, and throttle input more or less correlated to speed. The only problem encountered was a strange noise from the motors, and that was fixed by tightening a prop, and we were back to flying. The turning radius had to be pretty big, otherwise the wingtip would lightly scrape the ground. A quick way to fix this would be to map the altitude set point of the altitude controller to the current roll angle of the vehicle so that when turning, the altitude would increase to create more room for the wings. This would take about 5 minutes to add to my flight control code, but I was more interested in pressing on to get to the computer vision and autonomy portion of this project. But as you're about to see, maybe implementing this so I could have tighter turning would have been a good idea after all.
Good job, Nick. Great job.
Sorry!
That monkey.
Did it hurt?
Yeah.
You fell from heaven?
Oh, not then.
And the airplane hit you?
Yeah, it did.
Despite the little mishap, I finally had an RC Ekranoplan that flew identically to Kavin's larger version, so it was time to add a brain and some eyes. The brain is this Raspberry Pi 4 computer running robot operating system, and the eye is this wide-angle HD USB camera. I spent some time soldering parts together for a cleaner build and assembled the complete flight computer and microcontroller assembly that will ultimately splice in line with my or Kavin's flight controller. More on how that splicing works in a minute. I'm using these markers called AprilTags and a special detection algorithm on the Pi to reliably and accurately detect the target we want to follow. This algorithm isn't just identifying the tag and telling me it's to the left and right side of the image, but it's actually able to extract the complete position and orientation of the tag relative to the camera. Part of what makes this algorithm so accurate is the camera image rectification process, where we calibrate the camera with a known grid to remove the image distortion from the wide-angle lens. This is the same tag detection algorithm I used in my autonomous path planning drone project, which you should check out if you want to learn more about complex drone sensing and autonomy. I then used the AprilTag position estimate to write a rather simple controller to command throttle for speed and aileron for turning. Using the distance to the tag estimate and the lateral offset, I'm able to compute an error in pointing angle and follow distance that the controller uses. So long as the controller is always trying to point at the AprilTag, the Ekranoplan will always eventually end up right behind and following the target at a fixed desired distance. The Pi spits out the autonomy commands for throttle and turning whenever the AprilTag is in view of the camera, which are then read into this microcontroller. The microcontroller is also reading in the radio receiver signal that normally plugs straight into the flight controller so a pilot on the ground can fly. Whenever the computer detects a tag and computes a control output to follow it, that control output is summed with the radio command signal and sent back out to the flight controller. Essentially, the flight controller then just thinks it's being flown manually when in reality we've spliced in this new autonomous capability that can be turned on and off with a switch. So I mounted this all on my Ekranoplan and headed back out to the parking lot with my electric longboard and a giant AprilTag marker to tape to my leg while I ride around. My general approach was to get the Ekranoplan moving, then come up behind it with my longboard and sort of merge in front of it so it could lock onto the target and follow me. I couldn't do much maneuvering due to the size of the parking lot, so I ended up mainly doing a bunch of straight passes. My goal was to get the system tuned decently, and I did manage to definitely get it working, though it still had a little bit of trouble keeping behind me when the wind gusted. Part of what made getting this to work so difficult was the balance between video resolution to be able to track the target from far enough away and computation speed of the Pi. Basically, larger video resolution gave me better detections, but at the cost of lower frame rate and control bandwidth. I struck a balance at about 3 frames per second, which you're seeing here. And I apologize for the weird color flashing, my code to record the onboard videos still had some bugs. Being able to control my longboard remote with one hand and the Ekranoplan with the other hand and trust that it was following me was kinda weird, but really cool. My lightweight Ekranoplan was definitely still a bit too twitchy for the system to fully autonomously fly it, but I have a good feeling Kavin's 7-foot wingspan Ekranoplan he's been working on will be less twitchy and fly much better than mine. So I'm packing up this flight computer and camera and sending it to him over on the West Coast to see what he can do with it. Definitely go check out his channel and subscribe so you don't miss his video. I have no idea when it's coming because I literally just shipped this out to him, but he's got some really cool projects on his channel to keep you entertained in the meantime. If you like this video, I'd greatly appreciate a like and maybe even a subscription to my channel if you want to follow along with more projects like this in the future. This project was definitely a challenge and it took way longer than I anticipated, but it's awesome to know that other people are entertained and maybe even learning something new, so the effort is definitely worth it. Let me know what I should make next. Cheers.